Swayam Prabha. Digital India. Educated India.
So good morning and welcome back to NPTEL lecture series on classics in total synthesis. I think we have discussed about 100 total synthesis in this lecture series, and today the last lecture is going to be about total synthesis of a complex natural product called Zaragozic acid C. So the Zaragozic acid and squalestatins, okay, so both belong to the same family of naturally occurring fungal metabolites, were independently isolated and characterized by Merck groups and also from Glaxo. So these Zaragozic acids and squalestins were independently isolated by researchers at Merck and Glaxo. So they are potential inhibitors of squalene synthesis. Okay, so that means this could be used for the treatment of hypercholesterolemia. Okay, so those who have cholesterol problem could be potentially be treated by these naturally occurring compounds. Okay, so there are many Zaragozic acids, and that depends on the substituents at these two. One on oxygen, that is R2 attached to oxygen, other one that is the side chain R1. Okay, and if you look at these natural products carefully, you can easily find out 1, 2, 3, 4, 5, 6 stereogenic centers. Okay, and in that, how many quaternary centers are there? At least 4 quaternary centers. So it is not that easy to synthesize such complex molecule having 6 stereogenic centers and also having quaternary carbon atoms. Okay, so these are some of the squalestatin, Zaragozic acids isolated from the nature. And today what we will do, we will talk about the total synthesis of Zaragozic acid C reported by Eric Carreira's group. Okay, so this was the first total synthesis reported in 1995, and his idea was to use commercially available D-erythrolactone as a starting material and build upon the chiral centers present in erythrolactone. So this chiron approach based on the retrosynthesis, as you can see here, so this is the chiral starting material. Okay, this can be made in few steps from commercially available compound. So this, upon treatment with dimethylamine and methanol, one could open this 5-membered lactone to get the corresponding triol and amine. Now the triol, upon treatment with the protected 3-pentanone, and acidic condition, so you can see this 1,2-diol was protected as ketol. Okay, then sodium hydride benzyl bromide, you could remove this proton and benzylate the remaining secondary hydroxyl group, followed by treatment with 2-lithio vinyl ether. Okay, this is a vinyl ether, and at alpha position you can generate lithio by treating with n-butyl lithium or tertiary butyl lithium. So that will add to this wine drop like amide, and you will get corresponding enone. Okay. Then treatment of this enone with TMS acetylene grignard. So that will undergo highly stereoselective 1,2 addition to this enone to give the quaternary center. So now if you look at, there are 3 quaternary centers, 2 are carbon based quaternary center. So that one is achieved using this addition of TMS acetylene. Okay. Then one can ozonolize the double bond to get the ester, that is enol ether is ozonolized to get the ester, followed by reduction with sodium borohydride in methanol. The ester group is fully reduced to corresponding alcohol. So the 1,2-diol and the TMS group which is attached to the acetylene. So these are, this TMS group can be easily removed by treating with potassium carbonate methanol. Then the primary alcohol was protected as TBS ether. Then the secondary alcohol was in situ protected as TMS ether. As you know, between TBS and TMS, TMS is labile. So that is how you could prepare the intermediate A required for the total synthesis of Zaragozic acid C. Now for the synthesis of the other fragment aldehyde, he started with Evans chiral auxiliary and then attached the propionic acid anhydride. So then boron enolate followed by aldol reaction with this aldehyde. Okay, it's a classical Evans asymmetric aldol reaction gave this syn aldol. Okay. Now once this aldol is there, then the chiral auxiliary can be removed by treating with lithium hydroxide and hydrogen peroxide to get carboxylic acid. Okay. What's the next step? Reduction of the carboxylic acid with LAH gave the 1,3-diol. So the 1,3-diol, one is primary alcohol, other one is secondary alcohol. Okay. Then take this primary alcohol, tosylate, you get the primary tosylate. Now if you treat with phenyl lithium, okay, so the phenyl lithium, what it can do, it can remove this proton and then intramolecularly attack to form oxytane ring, followed by addition of another equivalent of phenyl lithium that can attack the oxytane and open the oxytane to get or introduce the phenyl group. So basically what has been done is to remove this hydroxyl group with a phenyl group. So you convert that hydroxyl group into a good leaving group, followed by treatment with phenyl lithium in the presence of Lewis acid, you can replace the hydroxyl group by phenyl. Okay. Then protect the hydroxyl group as piolate ester, then remove the benzyl group. Okay. Remove the benzyl group under hydrogenolysis to release the primary alcohol. This upon Swern oxidation gives the primary aldehyde. Okay. This upon Swern oxidation gives the side chain aldehyde B. Okay. So now we have seen the synthesis of fragment A and fragment B. Let us see the synthesis of the other O acyl side chain. So for that he started with this terminal alkyne. So this is easy to prepare in 3 steps from TMS acetylene. Then N-butyl lithium followed by quenching with formaldehyde, one can introduce this CH2OH. So first you remove this proton and then quench with formaldehyde. So that gives the CH2OH. Now LAH reduction, propargylic alcohol upon reduction with LAH give trans allelic alcohol. So that was done easily, and this trans allelic alcohol, once you have, this can undergo Sharpless asymmetric epoxidation. Okay. So the Sharpless asymmetric epoxidation with L plus diisopropyl tartrate gives this epoxide. Okay. So once you have this epoxide, that epoxide can be opened, particularly the epoxides derived from Sharpless condition on allelic alcohol, This can be easily opened with trimethyl aluminum. So now the aluminum will open opposite to this epoxide. So thereby one can easily get the anti-aldol product. If you look at this, it's like anti-aldol product. Now you have 1,2-diol. The 1,2-diol can be cleaved with sodium peroxide to get the corresponding aldehyde. This aldehyde, upon treatment with vinyl magnesium bromide, so you got the corresponding vinyl allylic alcohol. Okay. So this vinyl allylic alcohol, upon treatment with triethyl orthoacetate, okay, triethyl orthoacetate with a catalytic amount of acid, is well known to undergo Claisen rearrangement. Okay. So if that happens, you get this gamma delta unsaturated ester. Gamma delta unsaturated esters, whenever you see or wherever you see, one reaction which should come to your mind is Claisen rearrangement. So this is what the product. This is nothing but gamma delta unsaturated ester. Then simply you do the hydrolysis and get the carboxylic acid. So now you can see the 3 fragments A, B and C are ready. How these 3 fragments are combined to complete the total synthesis of Zaragozic acid C. So you start from the intermediate or the fragment A, and this fragment A, upon treatment with butyllithium, obviously this is the most acidic proton. You remove that proton and then form the corresponding lithium derivative, then add the fragment B. So fragment B has an aldehyde, so that undergoes intermolecular nucleophilic addition reaction to get this proporgelic alcohol. Okay. Once you have this proporgelic alcohol, one can easily oxidize that alcohol selectively using this Martin-Barodian reagent to get this alkynyl ketone, alpha beta unsaturated alkynyl ketone. And this can be reduced, the triple bond can be reduced under this condition, where the triple bond is reduced to trans double bond. Okay. The triple bond is reduced to the trans double bond. Now treatment with tetrabutyl ammonium fluoride removes both TMS and TBS to give diol. Okay. And you have this enone can be subjected to Sharpless asymmetric dihydroxylation. So the Sharpless asymmetric dihydroxylation gave this as the major product, where the 2 hydroxyl groups are coming from beta side and also some amount of alpha which is favoring the decide beta diol was obtained. The decide compound was taken and moved forward. So if you treat with HCl and methanol, what will happen? This whole group will go. So that will form a diol. Okay. That will form a diol, and this hydroxyl, okay, and this hydroxyl will form ketol with this carbonyl group to give this product. Now you can see the core structure of Zaragozic acid is formed. Okay. So what needs to be done? You have to attach the side chain at this carbon, and also selectively you have to remove this and then functionalize. These are 2 additional things to be done. So the free hydroxyls, that is the primary hydroxyl, this one and this one, were protected as TBS ether by treating with TBS chloride and then bases like triethylamine and 4-N-dimethylamino-pyridine. Now the secondary hydroxyl groups here were protected as piovolate ester by treating with piovolate chloride and DMAP. Then the benzyl group should be removed so that one can think about homologating at this carbon. So the benzyl group upon hydrogenolysis was removed to get the alcohol. Swan oxidation gave the ketone. Now addition of trimethylsilyl methyl lithium gave this product. See, normally when you talk about trimethylsilyl methyl lithium or corresponding magnesium salt, that is meant for Peterson olefination. Okay, you will get a double bond. So now, the product has trimethylsilyl ethanol as the subunit. So that compound, upon treatment with 18 crown 6 and potassium hexamethyl disaccharide, that underwent elimination to give the double bond. Basically, the whole thing is Peterson olefination. Okay. Then protect this hydroxyl group. During this Peterson olefination, one of the pyruvate ester also got hydrolyzed. So you have this free secondary hydroxyl group which was reprotected as TBS ether. Okay. Then he needs to functionalize this exocyclic double bond. Okay. But all the time what he got was this undesired diol and not the desired diol. So basically one has to do the dihydroxylation. So when you talk about dihydroxylation, the simplest method which will come to our mind is osmium tetroxide. When he tried with osmium tetroxide, only the 2 hydroxyl groups came from the convex side. Okay. So that is not the required one. So finally what he did, he went back to the ketone. Okay, he went back to the ketone. So instead of doing a Peterson olefination, he added lithium trimethylsilyl acetylide to get this as the major product. Now you can see this trimethylsilyl acetylene comes from the equatorial side, and this is the major product. You can see 6:1 ratio. So take this compound and then treat with silver nitrate to remove the TMS group attached to the triple bond. Okay. So the TMS was cleaved to get the triple bond, then diball reduction. You have 3 pyruvate esters. You have 3 pyruvate ester. All this can be removed by using diball. Reductive cleavage of the pyruvate esters are done with the diball to get a triol. Then treatment with acetic anhydride 4N dimethylaminoperidine gave the triacetate. Okay, TBS was removed and then reprotected as triacetate. So now you don't need this TBS group. Okay, you don't need this TBS. There are 2 TBS groups. Okay, this particular TBS, which is less hindered compared to the other one, was removed by treating with dichloroacetic acid. Okay, so that primary alcohol, as you can see here, you have the primary alcohol and the triple bond. So if you want to reduce the triple bond, you can do it under hydrogenolysis condition, so that the triple bond is reduced to the double bond. Now Des-Martin pyridine oxidation oxidizes the primary alcohol to aldehyde, which upon oxidation further under Pinnick oxidation condition gave the carboxylic acid. Basically the CH2OH is converted into carboxylic acid in 2 steps. Okay. Then came the esterification. This is one of the very rarely used esterification method, where the tertiary butyl esters are made like this from corresponding urea derivative. Okay. So once you have this tertiary butyl ester, the next step is to remove this TBS group. So that was done using HF pyridine, and next what one has to do is you have to attach the side chain here. Okay. And before that, this primary alcohol was oxidized under Des-Martin pyridine condition to get the aldehyde, and followed by oxidation and the Pinnick oxidation condition to get carboxylic acid. And that was again protected as tertiary butyl ester using the substituted urea derivative. Then ozonolysis of the vinyl group gave aldehyde, so that also was oxidized using Pinnick oxidation condition to get the carboxylic acid. Okay. Now if you look at this carefully, the third carboxylic acid also was esterified using the same method to get the tertiary butyl ester. He also used another method where he could start from here. That means he has a triple bond here and then 2 TBS protected primary alcohol. So what he did, first he reduced the triple bond to double bond. Then the TBS groups were removed using HF pyridine to get the primary alcohol. This primary alcohol, upon oxidation under Des-Martin pyridine condition, you could get 2 primary aldehyde, okay, 2 aldehydes. Then if you do Voss analysis, you will get 1 more aldehyde. Okay, so you can see there are 3 aldehydes at the end of this sequence. Now if you oxidize this under pinning oxidation condition, one could get the corresponding tricarboxylic acid. Okay. So now you can also protect all the 3 carboxylic acids in one step using this tertiary butyl urea derivative. Okay. So then what is required is you have to selectively carry out alkylation at this hydroxyl group. Okay. So potassium carbonate methanol will hydrolyze both the acetates to get the diol. Then this particular alcohol was protected as Bock ether. Okay. Then the other hydroxyl is free, so that other hydroxyl group was esterified with this gamma delta unsaturated carboxylic acid. This is esterified with gamma delta unsaturated carboxylic acid, which we already discussed how to make this gamma delta unsaturated carboxylic acid. So you can see this side chain was established, and here also on the right hand side chain was established. So what is left is to remove all the protecting groups. What are the protecting groups? There are 3 tertiary butyl groups. Okay, there are 3 tertiary butyl groups which should be hydrolyzed to get the corresponding tricarboxylic acid, and also there is one tertiary butyl oxycarbonyl group. Okay. So these 2 can be easily removed using trifluoroacetic acid condition. Okay. So that was done to obtain the natural product called Zaragozic acid C. So if you look at this synthesis, he started with commercially available T-erythrolactone. Okay. And overall he took about 25 steps, and yield was very good considering that it is a complex molecule, and then he and his group took 25 steps. 4.1% overall yield is a significant method, significant total synthesis among many complex natural products. So what I will do, I will stop here, and with this we have completed more than 100 total synthesis of really complex natural products, starting from very small natural product called illudane, and we went all the way to Zaragozic acid and many alkaloids. Okay. So with this lecture we completed the syllabus which I have proposed in the beginning of the course. So the last 2 lectures, it is basically to summarize what we have discussed. Okay, I am not going to talk about any more total synthesis in the next 2 lectures. That is the last 2 lectures. I will focus only on the synthesis which we have discussed, and that too each synthesis what are the key reactions we have discussed, so that you will get an idea of how many reactions which we have discussed throughout this course, okay, and how these reactions could be successfully used in the total synthesis of complex natural products. Okay. So thank you and all the best for your exams.